There we go. I will begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for the students. Just ask you to bless our work today. Help us to glorify you what we do. And just understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. All right, so we introduced notions of position, velocity, acceleration, and I've started to connect those to calculus. I'm going to make a stronger connection here in just a second by doing some examples. But one of the things I wanted to tell you before I get much further is just the rules of calculus at the level of vectors. And so I'll just entitle this little subsection Calculus of Paths. So basically here's the deal. If you have A and B, and these are like functions from, say, the reals to R3 or Rn, I'll say R3 for the sake of specificity, then we have various rules of calculus. For example, ddt of a constant times A plus B. Well, guess what? It's a constant times dA dt plus dB dt. So like we can differentiate the sum as the sum of the derivatives. The definition of the derivative of a vector valued path, just, let me just put that up here first, like dA dt. What does that even mean? Well, that means the vector dA1 dt, dA2 dt, dA3 dt. Now, I've talked about that mostly with regard to the concept of position, but the fact of the matter is you can differentiate any vector of functions of time just the same, right? There's a well-defined calculus there. It has this rule of linearity, but there's more. What else can we do? You guys tell me how's this going to go out. If I have ddt of like A dot B, how's that going to work? Care to guess?
Like one stays and then take the derivative plus derivative.
So I think you're telling me to do this. So this is the so-called product rule for the dot product. Notice that we're differentiating a function, right? A dot B is a function of time in this context, and the output is also a function of time, right? Okay, cool. Also, we can differentiate a cross product of functions of time. And the calculus here, this one matters a little bit more, that we maintain the order of things. All right, so like this is dA dt cross B plus A cross dB dt. So this is the product rule for the cross product. It'll be a while before we need to use this, but we'll use it eventually. Yep.
Would the dot product still be scalar, or would that be?
Well, A dot B is a function, and dA dt dot B is a function, dB dt is a function, but they're all scalar valued functions.
Okay, so they could still be scalar.
Yeah, this, on the other hand, vector, both sides, right? There is one other thing to think about. What if we have like a function times A? What happens if you differentiate? So f is a function of time, A is a vector of functions of time. How does that work out? Well, there is a product rule there as well, which is this, df dt times A plus f times dA dt. This is the product rule for a scalar multiple. Okay, that's pretty much it. The other thing I might mention is we also have a notion of integration, right? So like if I was to say integrate from, say, t1 to t2 of A of t dt, what that means is the integral from t1 to t2 of like A1 of t dt, integral from t1 to t2 of A2 of t dt. I regret doing this three-dimensionally, but at least I didn't do it n-dimensionally, right? Integral from t1 to t2 of A3. So an integral of a vector is a vector of integrals. Simple as. And we also have the concept of an indefinite integral. So if I was to say this, like integral of just A dt, a vector dt, that's also a thing, right? And essentially this is defined by the following: that ddt of the indefinite integral of vector a dt has to be equal to what? There's no dt after we differentiate. Like here, if I had ddx of the integral of f of x dx, what's that equal to? F of x, right. Same thing here, a. I suppose of t if you like. I mean, fine. Like, do we write the of t? Do we not write the of t? I go back and forth, okay? Just like sometimes we don't write the of x when we're talking about a function f, you know? Okay, so that's calculus of paths. Let me show you a specific example of this. Let us suppose that we have d squared r dt squared equals to a sub naught vector. So here I'm saying a sub naught is a constant vector. So what this means is that ddt of dr dt is equal to this constant vector. So what does this mean? What can we tell me about dr dt? Dr dt is equal to a time, t times a sub naught, plus some constant, let's call it c1. So when we integrate a vector equation, right, we're doing an indefinite integral here of a vector. I have to add a constant, but because it's a vector, I have to add a vector of constants. Yeah? Now what is this? What is dr dt? We defined it last time, right? If r is position, you're like, well, it depends what r is. Suppose r is position, right? If r is position, then if r is position, then the velocity is dr dt, right? And that in this case is time times the constant acceleration a naught plus a constant. But we don't usually write this formula in this way. Typically, we like to write the formula for velocity in terms of the initial velocity. So if the velocity is equal to v naught at t equals to 0, then we have v naught, right, is equal to 0 times a naught, right, plus c1, which is to say that c1 is equal to v naught. So getting to the point here, we have derived the formula, the velocity at time t is equal to v naught plus t times a naught in this situation. So there's my formula for velocity at time t, assuming that I'm starting with a constant acceleration. I'll get out of the way here in a second. Constant acceleration gives us velocity of this form. Time times the velocity, time times the acceleration vector plus the initial velocity. Then my next step, continuing this, is to go, oh, okay, so the velocity is also equal to the change in the position vector with respect to time, right? So if that's equal to v naught plus t times a naught, right? So I didn't write the integral sign in the last time. I just wrote an implication and said, hey, you integrate both sides, right? Let me be more explicit this time. You guys are fine. I'll write the integral this time. So integrate. Let's integrate this equation. So if I integrate dr dt is equal to the integral of v naught plus t a naught dt, right? And I'll stick with the indefinite integral for now. So this, the left-hand side here, that just gives me r at time t, let's say. What's the integral of v naught plus t a naught? So check this out. So first of all, integral of v naught is just t times v naught. Why is that? If you differentiate t times v naught, what do you get? You just get back v naught, right? If I differentiate what I just wrote down, we'll get back v sub naught, that constant vector. What do I need to write down here? How about this? Plus 1/2 t squared a sub naught vector, right? If I differentiate that, that gets me back to t times a sub naught. All right? Yeah.
You're able to do that because acceleration is constant.
Because, yeah, exactly, because acceleration is constant. If acceleration is not constant, it's another ballgame. Now, we're integrating both sides. I'm doing an indefinite integral at the moment, so I'm obligated to add plus c2, right? Plus c2. Now, great. So then, if I'm given that the position at time 0 is equal to r sub 0, as is our typical kind of notation here, then what does that mean? Yep.
Why is it C2 and not like C1?
I already used C1 over here. So then r of 0 is equal to 0 times v naught plus 0 times a naught plus C2. Therefore, C2 is equal to r sub naught. Right? C1 was v sub naught, as it turns out. So then I'll put it all together. What do we got? We have the position at time t is equal to r sub naught plus t times v sub naught plus 1/2 t squared a sub naught. So there you go. These are the vector formulas for constant acceleration motion. All right? And I've based the formulas at time 0, right? What if you had data at some other time? How could you kind of come to terms with that? So like, let's suppose that the acceleration is not constant, you know? So what if the acceleration was equal to, say, like t times j, where j is constant, right? And suppose we know that the velocity at time 1 is v1, and the velocity, excuse me, the position at time t1 is r sub 1, right? These are given. So then my question is to find, you know, the position, the velocity, you know, at time t. Let me recast that for a second here. Find the position and the velocity at time t. So I'm going to do the calculus a slightly different way this time to illustrate. We have two different methods to integrate. The one is to do an indefinite integral and then to fit the constant. But the other way is to do definite integrals with bounds that, you know, well, I'll just show you. Let me just do it. So, like I have to start with here, a is actually dv dt, right? So I have dv dt is equal to t times the j vector. Right? That's from this. So my first move is to integrate this. All right? But this time I'm going to do a definite integral. I'm going to integrate this from, say, t1 to t2, dv dt, and that's going to be equal to the integral from t1 to t2 of t times j vector dt. What's the integral of dv dt? So the left-hand side, essentially by the fundamental theorem of calculus, which still holds for vectors. This gives us v of t2 minus v of t1. Maybe you called that the net change theorem in calculus, right? This is the net change theorem for a derivative of a path. Now, what's the integral of tj? Yeah, we've got 1/2, so 1/2 t squared j vector, and I'm supposed to evaluate that from t equals t1 to t equals to t2. I wrote down this step this time. Let me do that. So that's 1/2 t2 squared j minus 1/2 t1 squared j. All right, so let me put this all together here. I'm gonna pick up the story over here. Okay, so this gives me, I'm gonna let t2 equals to t, and if I do that, I find the following: the velocity at time t is equal to v sub 1 plus 1/2 t squared minus t1 squared times the j vector. See, because we're given that the velocity at time 1 is v1, right? And there's a common j, I can factor it out. I can do algebra there. And I'm just saying t2 equals to t, all right? So I've got that. So next up, I have v is equal to dr dt, right? And then I want to integrate what I just boxed. I'm going to integrate it from time 1 to time 2. So I've got the integral from time 1 to time 2 of dr dt dt equals the integral from time 1 to time 2 of v1 plus 1/2 t squared minus t1 squared j, close parentheses dt. I got to do this integral. All right. I'm going to write the answer like way over there, but so that gives me, and this is from the previous example, so let me box this off here. I probably should just erase that if I knew what's good for me, but I'm not that smart. See here, so we have r of t2 minus r of t1 is equal to, well, I have to do this integral, right? So when I integrate v1, that ends up giving me t2 minus t1 times v1. That's what I get from this piece right here. How about the other piece? How does that integrate? Let me find some color here. This piece here, let's think about this. This is going to integrate to, let's see here. I guess I'll leave the half out front. And that's going to give me a 1/3 t2 cubed minus t1 cubed. That's the integral of the first piece. And then I've got minus t1 squared times t2 minus t1. And all of that, it's got the j on it. So finishing blow here, let me write the answer. What we get is r at time t is equal to r1 plus t minus t1 times v1 plus 1/2 of 1/3 t cubed minus t1 cubed minus t1 squared times t minus t1 all times j. And that is the formula for the position at time t, assuming that the acceleration is t times j, the initial position is r1, the initial velocity is v1. All right? So I wanted, you see the contrast in methods here? For example 1, I did an indefinite integral to like resolve the derivatives, and then I fit the constant to fit the data, right? In contrast, in example 2, I do integral from t1 to t2, and then after I'm done with that, I put t equals to t2 to discover the formula as a function of time. I don't know why this chair is here. My apologies. Oh, goodness gracious. All right. Do you guys know what the derivative of the acceleration is called? The jerk, right? What's the derivative of the acceleration here? See this? So dA dt for this example was j, right? So example 2 is actually the constant jerk formulas. So jerk is like, you feel that if you're, for example, one place where you can feel it is if you're on a train or something and you go from a straight track to a curved track, like maybe an amusement park or something, you know, like those little toy trains, they'll have like a straight track and then a curved track. And as you go from the straight to the curved, all of a sudden you feel this like jarring, like, that's an example of non-trivial jerk. It's sort of a discontinuity in the acceleration in some sense. Okay, so there's that. Now, sorry, I'm trying to find my notes. So what I was going to show you guys next here is drop back here to one dimension for a second. So we're roughly speaking around page 39 of my notes, give or take. So let's talk about one-dimensional motion here for a bit. So one-dimensional is a little bit easier, right? So there, if we have acceleration is equal to, let's use x in the x direction, right? So if a is equal to a naught is equal to d squared x dt squared, right? And that's also equal to dv dt. Then going through the same calculus I just went through, what do we find? So we find, among other things, we find that the velocity is equal to v naught plus a naught times t, right? And then if we integrate again, we find that the position is equal to the initial position plus v naught t plus 1/2 a naught t squared, right? So these are the, famed constant acceleration formulas. All right? Now, a good... Oh, you did? Yeah? Oh, thanks. Muchas gracias. I only know Sesame Street. So, yeah. Okay, so I know just enough to be offensive, pretty much. But so, sorry. Let me stop with my microaggressions and/or medium-sized aggressions. I'll behave. So, check this out. There's a bunch of different things we can say about one-dimensional motion, constant acceleration, right? So one thing is if we draw a graph of time versus velocity, that's pretty nice. If we start, we have like the initial velocity is v naught, right? And if we're talking about positive acceleration, then the graph looks something like this, right? This is v naught plus a naught t. So the slope of that line would be the acceleration, right? So another thing you might notice, and there are problems which require this to solve, is that there's this cool kind of relation between, say, if we say T1 here and T2, right? So we're talking about velocity 1 and velocity 2, right? What's the area under this graph mean? Position. So the area here is equal to the integral from T1 to T2 of dx dt, which is x of T2 minus x of T1. So that's not quite position. This is the change in position, right? This is the displacement from time 1 to time 2. Okay? So that's one thing. That's the displacement. But what else is the area? What's the area of a, what's this? Is this a trapezoid? What's the formula for that? V1 plus V2 divided by 2 times what? Times the T2 minus T1, right? Times the change in time. So this distance here, change in time, right? And if you take the average, that gives you the box of the same height, which would have the same area as the parallelogram, right? Excuse me, trapezoid. My bad. So, hey, this is sometimes a useful, but we can rewrite this. This says that change in x over change in t is equal to v1 plus v2 over 2. So this is the average velocity, right? Average velocity. And this is the average of the velocities. Seems like I said nothing, but I actually said something quite profound. There's a very big difference between average velocity and average of the velocities. Do you see the difference? If I tell you you have 10 meters per second and you have 20 meters per second, what's the average velocity? The answer is 15 meters per second, right? So, what's the delta t in that situation? That doesn't even make sense, right? I can take the average of two numbers. One of you has an 80 on the test, the other one who has a 90 on the test. Together you have an 85 average, right? That's a very different notion of average than this. Average velocity is change in displacement over, change in position over change in time. Okay, so that's one. This is sometimes very helpful. Another thing to notice is that if we look at, this is a kind of a trick, but we have dv dt, and this is just okay, so this trick is not special to the constant acceleration case. Like this same thing is very useful for other problems in one dimension. So check this out. If we're in one dimension, we can rewrite dv dt as dv dx times dx dt by the chain rule. But this is to say, this is one of my favorite things to say, and oh, my bad, I should write this first. So that's v, right? This is v. So we've got v dv dx, or as I like to say, v dv dx. So the acceleration in one dimension can be rewritten as v dv dx. This is super awesome. If it's a constant acceleration, right? So suppose this. Because then we can do things like, so v dv is equal to a naught dx, right? And then we can separate variables and we can integrate. So it's customary when we do that to integrate from v naught to vf, integrate this from x naught to xf. So that's the change of variables theorem. If on the left-hand side I'm integrating with respect to velocity, on the right-hand side I need to integrate with respect to position. These are matching, they're tied together, right? The velocity at position x naught is v naught. The velocity at position xf is vf. But we can do these integrals, right? And these integrals give us 1/2 vf squared minus v naught squared is equal to a sub naught times xf minus x naught. Or, if you like, and I do like to write it this way, we get vf squared equals to v naught squared plus 2a naught delta x. This is our beloved timeless equation. It is super useful when you're trying to solve constant acceleration problems. Why is it called the timeless equation? It's not particularly profound. It's got no time, right? So, yeah. This is actually conservation of energy, as we'll learn in about 3 weeks or so. But for now, it's the timeless equation. Great, so that's your one-dimensional motion, constant acceleration short course right there. Graphing position, graphing velocity and time, the area being position, change in position rather. This is rather special for one dimension, right? I can't draw this graph for my example 1 and example 2, right? It's a 3-dimensional situation. So like that kind of graphical question really just arises in 1 dimension. So I'm going to jump back to 3 dimensions again here. So just to let you know where we're going, today I'm going to spend the rest of class talking about how acceleration and velocity are related geometrically. And once we're done with that, we will, next class probably, talk about projectile motion. So technically speaking, I've kind of a little bit off my planner a little bit, but so next time we'll talk about projectile motion most likely. But I think logically speaking, what I'm about to talk about goes right here, best. So I'll entitle this little section here, Geometry of Acceleration and Velocity for Paths. And if we have time, I'll also talk about a little bit about circular motion here. All right, so let's start at the beginning. I'll draw a picture. Talking about a 3-dimensional path, all right? So it goes somewhere, wherever it's going, it's in 3 dimensions. So I can picture it here in the XYZ coordinate system, right? And I can imagine, drawing the position vector here at time t, right? Or I could draw the position vector at a different time over here, right? So this is the position at time t. And so I'm imagining, we draw a little arrow here on this path to indicate that the motion of the object is like along that way, all right? So first order of business is to understand how velocity figures into all this. So velocity is dr dt, right? And I tried to describe to you guys a little bit the other day what that looks like. So forget my color coding. Sadly, I don't have a color printer, so I can't properly envision this, but I think I used green for the tangent vector. So we can picture the velocity as like a little vector that points in the direction of motion like this, okay? So here's my v. So that's velocity. Oh man. So we got that. Then we can calculate acceleration. So one more point. This we can write as the speed times, I'm going to introduce a new notation, if that's okay with you guys. Well, even if it's not, I'm going to do it. Big T. Big T is the only unit vector I draw without a hat. So big T technically is v hat. It is a unit vector in the direction of the velocity. It's also known as the unit tangent field. The unit tangent field. So this is speed, right? And this is basically direction, right? This is the direction of the path. And that changes with time, right? What happens if we differentiate this? If we differentiate this, we get acceleration. Acceleration is dv dt. So that is d dt of the speed times the unit tangent. This is a scalar function times a vector function. We need the product rule that I have now erased, right? And so how does that go? This gives us dv dt times t plus v times dt dt. All right? And so that might not seem like much, but we can prove that these two vectors here, t and dt dt, are actually perpendicular. These are perpendicular vectors. Now you might say, how do you know that? Let me show you how. So the way we know that is t is a unit vector, right? So t dot t is equal to what? 1, right? Because that's the length of t squared. Now differentiate that. Differentiate it with respect to t. What do you get? Well, yeah, let's say we get t prime. Here, let me hand this handy dandy attendance sheet out. I seem to have, if you could add a date to it, that would be wonderful. Sorry. You know, just as soon as I'm not distracted in here by like a board being missing or other things, I'll top hat. As soon as I have undistracted day, we will top hat. I promise, it's coming. It'll happen eventually. Until then, I hope this satisfies your attendance needs. Yes? Check the box. Think of it, imagine it being top hat. Okay? So if we differentiate this, we give t prime dot t plus t dot t prime equals to, what's the derivative of 1? Well, it's 0, right? So what's this tell me? It tells me that t is perpendicular to, let's say, dt dt. If you want me, t prime is dt dt, all right? So, definition, big N is equal to 1 over the magnitude of dt dt times dt dt. This is called the unit normal to the motion. This is a unit vector. Why? Because I'm dividing by the length of dt dt. So this is by construction a vector of length 1. And I can picture this. What this ends up doing is it points towards the center of the radius of curvature for the motion. So it's like, it's perpendicular to the velocity. It might look something like this. Right? Perpendicular. And then you're like, well, please define more things. It always makes me happy when you define more things. I'm glad that you asked. So here's the other thing. The binormal, B, is t cross n. This is the binormal. That's perpendicular to the tangent and the normal. So in my picture over here, right-hand rule, V crossed n, it's like into the board here-ish. Right? V cross n, I guess it's kind of into the board. I can't draw it. I can't draw it with anything. It might help for me. Let me draw it here. It's easier to see if I do it like here. I'll just draw the curve as if it's in the plane of the board. So the velocity vector would look like this. You know, the unit tangent vector would look like this. The normal vector points towards the circular, the center of the radius of curvature here. So over here, if we're continuing, if this is the tangent, then the unit normal points like this. In this case, so let's think about where's the binormal. T cross n, so the binormal's into the board. T cross to n, binormal's out of the board there. All right. So what this the TNB frame is an example of a right-handed frame. TNB is right-handed. It's a right-handed frame. Frame, what that means is it's a collection of vectors thought of at once. All right. So this is the so-called Frenet frame. And you could use it to set up a coordinate system that moves with you. If you wanted to, you could like define coordinates that move with the particle and use t, like you could use t to set up the x coordinate, n to set up the y coordinate, b to set up the z coordinate if you wanted to. Yeah. Ah, we're getting there. So it turns out that when you study the Frenet frame, they have to satisfy these equations that are known as the Frenet-Serre equations. The Frenet-Serre equations relate the, let me write them down here. So I won't derive them in here because this isn't, the right place, but I will state them for you. They state the following. dt is v times kappa t, and dn dt is minus v kappa t plus v tau b. And finally, dB dt, so these are page 35 of my notes, if you're wondering, minus v tau n. So these are the so-called Frenet-Serre equations. All right? So if you look back here at my formula for acceleration, let's take another look at it. What does it say? It says acceleration is equal to dv dt times t, right? Plus v times dt dt. What's dt dt? dt dt, according to the Frenet-Serre equations, is equal to v kappa times t. Now I'll tell you what that is. Kappa here is by definition the curvature. It's the curvature of the curve. The curvature is related to the radius. So if you fit a circle, right? If you can imagine the osculating circle, which is like a circle that just fits in the curve like this here. All right, the radius of this curvature, kappa, is basically 1 over that r. If you fit a circle to the curvature is the reciprocal of that circle, that osculating circle. And so what this says is that the acceleration, I'm actually getting to something here, guys, believe it or not. Did I say, oh man, I typed that down wrong. That's supposed to be an n. My notes have an n here. That's important. The reason that's important is now we have plus v squared over the radius of curvature times n. And that is a formula for the acceleration that breaks it into two pieces. There's a tangential part to the acceleration, and there's a centripetal part to the acceleration, or you could say normal. I think I lost a minus maybe. No, it's fine. So this is the tangential component to the acceleration, and this is the center-seeking component to the acceleration, right? Notice that t and n are perpendicular, so this means the magnitude of the acceleration is simply the square root of dv dt squared plus v squared over r, quantity squared. This will be important to us as we study circular motion, all right? So, yeah, I mean, this is important because it gives us an understanding of what is the geometry of the acceleration. Like, generally speaking, the acceleration has two pieces. One piece is in the tangential direction, and the other piece is in the normal direction. Basically, the piece that's in the normal direction is responsible for changing the direction of motion, whereas the piece in the tangential direction is responsible for speeding up or slowing down the motion, as is reflected by the fact that you got dv dt here. So, and you guys are seeming restless. I must be over time. So, my apologies. I will eventually end on time. Thank you, guys.